So in the previous session, we discussed about the existence of a finite cyclic group. We discussed about the existence of infinite non-cyclic group. Infinite non-cyclic group. Let us now check two more cases to either disprove or prove the existence of other two cases that was written in the previous session. For that, I'm going to consider one another example where I'm going to take a set capital G which contains elements, 4 elements of this form. The elements are given as E, A, B, C. I shall define a special operation star on the set capital G, and that will be defined in the following manner. This operation star can be defined in the following manner. Now, remember one thing, that whenever we whenever we actually design a structure by defining some sort of binary operation on the set, on the non-empty set, then this operation is considered is not always the algebraic operations like addition, subtraction, multiplication, and division. These operations can be anything. If I consider a set with 2 elements, I can define an operation like max of the elements, max of 2 elements. I'm considering the set containing several elements, say, then I can define the element as maximum of 2 elements. That can also be a kind of operation, because it is a binary operation. Obviously, it is a binary operation. To find the maximum, you have to if you have to choose 2 elements at a time, that is how the operation is defined, and try to find out which one is bigger. That is also a kind of operation, but this is not a kind of algebraic operation that we usually know, that like plus, minus, division, and multiplication. So this operation star that we define on the different sets, they are not always the usual operations of addition, subtraction, multiplication, and division. For this set capital G, I'm going to define this operation star in a special way. And for this, I'm going to construct a table. The table is constructed in the following manner. First of all, we draw a line like this, a vertical and horizontal line like this. And on the column headings, I am putting the elements as E, A, B, C. And row headings are considered as same. Now I'm defining the elements. I'm putting the elements in a special way, not just in arbitrary way. So in the diagonal, I am writing it as E, 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 E. Okay, so that means when E is getting, when we want to calculate E star E, we get E. So it means what? It means E star E is equal to E. This column, this particular value means A star E, A star A is equal to E. Second, I have written, third, I have written B star B equal to E, and C star C is equal to E. In this manner, I have defined the diagonal elements. Then we are going to put the non-diagonal elements in a special way. I'm going to write here A, B, C. I'm going to write here A, B, C. And here also I'm going to write A, B, C. And then we are going to put we are going to fill other blank spaces in the following manner. I have used multicolors to write these elements because intentionally, so that some kind of structural parity that you can observe. All the diagonal elements have been written in blue color. All the elements are written over here in pink color, here also in pink color. And this element B is written in black color, and other elements CA, CA are written in the brown color. So just checks kind of some kind of structures have been given to this particular table. In this manner, I have defined the table. And this is my operation. This is the operation by which I have defined it. You can ask me how quickly where are you able to write this? How quickly can you give us this particular operation? Because we have to think a lot to identify this. It is because this particular operation or this particular group that I have considered over here, it's a special group, and those who know abstract algebra, they are familiar with this particular group. So actually I am memorizing the group and I'm actually writing it over here. So once you learn the group, then you will be able to memorize this also, only if you can know the structure of this particular group. Now, from this multiplication table, you can easily verify that I'm not going to discuss in details, that this group, this set G under this operation is not only a group, it is also a commutative group or an abelian group. It is a commutative group or abelian group. Okay, such a group has a special name, and the name of this group is, in group theory, is called Klein's 4 group. The group has a special name. It is called Klein's 4 group. Sometimes it is defined as, this group G is defined as K4. K4 in some books. Now you can easily check that. Now suppose you are going to choose the element E from this group. You will find that the elements generated by E will just be the element E itself. You try to assume different integers over here and raise the element to that power. You will find only that element, small e. So E is actually giving you the element E itself. So obviously the element E is not a generator of the group, is not a generator of the Klein 4 group. Now, if I consider the element A, just look at the chart and verify that A only generates the elements E and A. No power of A gives you B, and no power of A gives you C. Only this set EA is being generated by A. Okay. Again, you can look in the group that if I consider the set, the element B is generating only the element E and B itself. No power of B is generating A, no power of B is generating C. And similarly, C generates the element E and itself. No power of C generates A, no power of C generates B. So we are seeing that in this particular group, there exists no element which can generate the entire group. Just like small I and minus I, the imaginary I and minus I generates the entire an entire G, that is a set of the roots of the equation x to the power 4 equals to 1. Here I am unable to find any such element which can generate all the elements of this particular set under the operation, obviously under the operation star defined over here. So this shows that G is a finite group, but it is non-cyclic. G is not a cyclic group. Okay, so I have shown you over here by an example that there are groups which are finite non-cyclic groups. Finite non-cyclic groups. 3 examples so far has been shown to you, one of which is this one, another is 2, and another is 3. The last one is 3. You have to remember these examples. But another observation which comes from the discussion of this Kleins 4 group is that try to look at this group carefully. What we have observed, we have considered a finite group with 4 elements, operations defined in a special way, and the group is not cyclic. It's not being, the elements of the group is not being generated by any of the 4 elements. But you can check that another fact from here, that the set EA, the set EB, the set EC, these 3 sets, and obviously the trivial one, are subgroups of the group capital G. All the characteristics, characteristics of subgroups will be satisfied by these elements containing two numbers, or the singleton set is always a subgroup, trivial subgroup. This is the trivial subgroup, but we can write it in this manner, that small e is the trivial subgroup, but other 3 subgroups EA, EB, and EC are non-trivial subgroups. Non-trivial subgroups. But if you observe further carefully, you will find that this non-trivial subgroup EA is being generated by the element A. This non-trivial subgroup EB is being generated by the element B. This non-trivial subgroup EC is being generated by the element C. So from this Kleins 4's example, we have also come to know of another fact, very important fact, which is there exists a group which is not cyclic, but its non-trivial subgroups are cyclic. Very important fact. From there, you can online questions can MCQ type of questions may be asked. So you have to remember: does there exist a group which has non-trivial cyclic groups, but as subgroups, but the group is not a cyclic itself? The answer is yes. So answer is the Kleins 4 group is such a group. The Kleins 4 group is such a group. Okay, so this is a very important example. One more thing is remaining that I'm going to leave for you to find out, to think by yourself, or try to look for this result in the book or in the internet. I have proved the existence of finite cyclic group. I have proved the existence of infinite cyclic group and finite non-cyclic group. What about the existence of infinite cyclic group? Do they exist? If they exist, try to give an example of that group. And if such a group exists and they are cyclic, then obviously they must have a generator. Then you can have to identify the generator of such groups also. I'm going to leave that for you. You just try to find out by yourself. Okay. Now there are some important results which are often used in the topic of cyclic groups. These results are actually I am going to write those results in terms of theorems, but I'll ask you not to try these theorems. You don't have to write the proofs of these theorems because for the current scenario, the proofs will not be required Other, if it were a physical of classes and you are like supposed to sit for physical offline examination, then I would have suggested you to go for the proofs. But right now it is not required because you know how the questions will be set. So with respect to the current scenario, I am only going to give you the statement of these theorems because these theorems are very important and they help us to solve problems. So right now I'm going to write the statements of the theorem one after another. Two theorems have already been given to you. One theorem is that every subgroup of a cyclic group is cyclic. This is a theorem. You can consider that as theorem 1. Theorem 2 that I have given you is that every cyclic group is commutative group or abelian group. Okay, so that you can consider as theorem 2. Now the other theorems you can name it as theorem 3 that I'm going to write the statement of that. If and only if means by implication, means it is both way true. This is the a finite group capital G is a cyclic group if and only if there exists an element A belonging to G, so that order of A is equal to order of the group. Or if such a thing happens, then you will find that the order of the uh, if order of an element is equal to the order of the group, then you can immediately say that the group G is a cyclic group. And this theorem has a corollary that I'm going to write over here. The corollary is saying that let generator A be a finite cyclic group, then order of A is equal to order of the generator of A. Same thing, because if A is the generator, then actually this is equal to capital G, and the same thing has been written over here. Just try to look at this. So I am just giving you the two forms by which this theorem can be stated. Okay, anyways, now next theorem, which is also very important, goes like this. Let capital G is a group which is generated by A, that is be a cyclic group of order n. Okay, then for any integer small k where 1 less than or equal to k less than n, a to the power k is a generator of capital G if and only if and only if GCD or greatest common divisor of the number small n and k is equal to 1. It's a very important result. All these results will be applicable to different problems. We have these results with us. So depending upon the problem, we can choose a respective result and we can try to find out whether we can reach to any solution by applying these theorems. Another theorem which is very important, very important, goes like this. Let G equals to generator A be a cyclic group of order n, So this theorem has two parts. Part one is that if H is a subgroup, of the group capital G, then order of H divides order of G. And number two, if small m is a positive integer such that m divides n, then there exists a unique subgroup of G of order m. Now I'm asking the students who are taking snapshots to quickly take the snapshot of this particular page, because I'm going to show you one of the I'm going to show you a problem where you can see one of the applications of these theorems. Okay, so just quickly take the snapshot and I'm going to show you a problem where one of these theorems will be applied. I'm going to show you a problem where the theorem 5 will be applied. Okay, so let us see what comes out of it. I'm moving on to the next page. Question is, suppose capital G is a cyclic group such that capital G has exactly 3 subgroups, namely capital G, E, these are trivial subgroups, and a subgroup of order 5. Then order of G is, option number A is 5, option number B is 10, option number C is 25, option number D is 125. So by seeing this, you can identify what sort of problems can be asked in the examination. Also, there I want to make a cautionary statement to all of you. When I take an examination, I have seen that you are in a habit to find out the solution in the websites like Stack Exchange and Quora. Okay, and you try to get solutions from there and put it in the answer section. But if you do this, if you try to find out, if you are using your desktop, you can copy this particular question to Quora, and in Stack Exchange, sorry, not Stock Exchange, slip of tongue, Stack Exchange, some sort of solutions will be given over there. But do not blindly follow these solutions, because these solutions are written in such a vague manner and in such not elaborated in these websites, that often there is a high probability that you may become misled. So since this abstract algebra or this type of or like real analysis or topics like linear algebra, these topics are actually part of pure mathematics. So try to find out your own logic and try to solve these problems. Do not go for the solutions, because even if you find the solutions, they may not be elaborate and explicit. So I am going to show you one such example and try to note this particular theorem 5, because I'm declaring that I'm going to take the help of this theorem in this particular problem. So I'm going to just show you how am I going to take the help of that. G, it is given that the cyclic group G has exactly 3 subgroups. Okay. G is cyclic, remember. These subgroups are the group itself, the singleton identity, and another subgroup H of G, where order of H is equal to 5. Now, case A, I'm going to study whether this is a correct reply or not. Suppose order of G or cardinality of G is equal to 5. Okay. Now, in this case, the cardinality of this subgroup, that is E is a trivial subgroup, which is equal to 1, divides the order of the group, because order of the subgroup divides the order of the group, we know from the theorem. Also, cardinality of G, which is 5 according to our assumption, divides itself. Now, from this theorem also we know, from the second part of the theorem, look at the second part of the theorem, we also know that this set capital G has exactly 2 subgroups. Therefore, in which case the subgroup which we have denoted by H is exactly equal to the group itself. But this is a contradiction. Why? Because it is given that G has exactly 3 subgroups. Contradiction to the given condition. Contradiction to the given condition. Why is it so? Because it is written in the second part that if M is a positive integer such that M divides N, there exists a unique subgroup. There exists a unique subgroup of G of order M. Here, let us choose M to be 1, and here let us choose M to be 5. So, since 1 is dividing 5 and 5 is dividing 5, there is a unique subgroup of order 1, there is a unique subgroup of order 5. These unique subgroups are nothing but singleton E and G itself. No other divisors of 5 exist, and therefore, what about the existence of capital H? But you have told us that capital G has exactly 3 subgroups. Then, if this is the scenario, this capital H must be equal to capital G. There are no other way out. So therefore, this is a contradiction, because in this scenario, your group G has only 2 subgroups, exactly 2 subgroups. What about case B? Let us assume that order of the group is equal to 10. Okay. Now, the divisors of 10 are 1, 10, 5, and 2. So you can consider this to be, suppose this is your M1, this is your M2, this is your M3, and this is your M4. No problem. Now the second part of the theorem, the previous theorem says that we must have a subgroup of order 1. We have this. We must have a subgroup of order 10. We have this. We must have a subgroup of order 5. We have this by the given condition. What about this one? What about this one? The theorem, according to the theorem, we must have a subgroup H1 of order 2, but H1 must have unique H1 of order 2. And if it is so, then G has exactly 4 subgroups, but it is a contradiction. This thing is a contradiction, and therefore your answer cannot be B also. So this is wrong. This is wrong. Okay. Let us go to case C. Suppose order of G is equal to 25. Then the divisors of G are, or order of G are 1, 25, and 5. Now, just like the previous example, we can consider a trivial subgroup of order 1, which is E, a trivial subgroup of order 25, which is G, a non-trivial subgroup of order 5, which is given, which is H. And therefore, no other subgroups exist if we consider the order of the group to be 25. And this is the thing which is valid, and therefore this particular statement is true. So 25 is the answer. What about the last one? Case D. If capital G is equal to 125, then the divisors of cardinality of capital G are 1, 25, 5, 125. Now the same problem is coming out over here. Corresponding to this number, we have the group G. Corresponding to this number, we have the group E, singleton E. For this number, we have H. But what about this? No subgroup of this order, or no unique subgroup of this order. Okay, and therefore this cannot be your answer. So if this problem is given to you, the answer to the solution, answer to the problem is given as option number C. So here in this particular problem, I have shown you that how to utilize the theorems which I have given over here to find out the solutions of the given problem. Okay, so theorems are important. The proofs are important, but at present we will just concentrate on the theorem, the statement of the theorem. If the proof is short, then I will try to show that to you. But if the proof is too long, I will suggest you to skip the proof and to get a problem in which the proof can be, the statement of the theorem can be applied. I think for the online examination, we have to give more concentration on the short problems, not for the long proofs. I think you are also agreeing with me. So in this particular session, in this particular two sessions that I have taken today, I have given you one homework, which is this, that you are going to find out by yourself, that does there exist an infinite cyclic group. Another homework that I'd like to give you is the following. So it is a homework also to try to solve it, try to find out the solution of that. The problem is like this. We have shown that Q plus is not a cyclic group, R plus is not a cyclic group. Now, to you, I am giving you a problem. It is not a theorem. Since I'm writing proof there, don't think I'm going to give you a theorem here. Prove that any finitely generated subgroup of Q plus is cyclic. Try to try to prove this particular result. This proof is very simple. Just give a little thought. You can consult book, you can find out solutions in the internet, whatever, but try to do it by yourself. So I can just take the initiative. I can just give you a hint how to start with writing this particular proof of this particular theorem. Finitely generated subgroup. Okay, so what you are supposed to do is that you are going to consider that let H be any finitely generated subgroup of Q plus. Okay, and suppose you consider this. Suppose this H is being generated by the following set: P1 by Q1, P2 by Q2, Pn by Qn. By this finite set, H is being generated. If a particular set is generated by a finite set, then the set is called the finitely generated set. So that means what? If we consider an element belonging to H, this implies this element X can be written as K1 into P1 by Q1 plus K2 into P2 by Q2 plus Kn Pn by Qn for some integers K1, K2, Kn belonging to Z. This is your hint. So I have started the engine, you drag it on and finish the proof. I hope the main important part of this particular problem, that is the main important concept of this particular problem, has already been told to you, which is what do we mean by finitely generated thing? What do we mean by this? So that has been explained. Now what you have got the car started. Now you have to drag it on to the finishing line. So steer it up, try to complete the proof. Also try to find out the existence of or non-existence of the infinite cyclic group. And tomorrow I'm going to hear from you in our session, which will be taken at 6:30. And because I'm engaged, as I have told, I'm engaged in this faculty development program. For this, I have to change my schedule, and this is only meant for this week. So sorry for the inconvenience. Hope to meet you tomorrow at 6:30. Okay, and till then, bye. Hope you have understood today's class. If you have any doubt, you can ping me in the WhatsApp. Take a snapshot.